Greetings and welcome back. Today we'll be looking at further addition-elimination reactions, particularly involving esters, but also related molecules such as carboxylic acids and amides. Right, so going back to our addition-elimination reactions in general, we looked at recently the reactions of acid chlorides, which look like this. And nucleophiles in general can come in, kick electrons up to the O, come back down again. This is that slingshot mechanism, and kick off the chlorine. And they can do that very easily, and this is a very reactive functional group, the acid chloride, largely because the chlorine is a very good leaving group. So when we consider esters as well as related molecules, the OR itself is not a tremendously good leaving group, and furthermore, there is resonance, which helps to stabilize esters and keeps them from being too reactive. So in other words, these guys over here are incredibly reactive, whereas esters are not quite as reactive. So we'll look at the reactions of esters, including some addition and elimination reactions, and that will be what we're doing today. So I want to start off looking at what can happen in the case of our extremely strong nucleophiles. That is to say the Grignard, which is RMGX/alkyl lithium, as well as the extremely strong hydrogen nucleophiles, lithium aluminum hydride and sodium borohydride. So you may recall that these guys reacted very, very strongly with acid chlorides in that they would react twice, one time kicking off the chlorine and the second time adding to the resulting ketone or aldehyde. And the same thing is going to happen with these three to an ester. So let's look at some specific examples. If I start off with this ester, OCH2CH3, and I add in, let's just go with a benzene ring Grignard reagent. The Grignard is a very strong nucleophile, and so therefore this Grignard will attack that carbon, kick electrons up to the O, they'll come back down again, and they'll kick off that oxygen. So again, like I mentioned before, esters are not very reactive compared to the acid chlorides, but you're trading off a carbon nucleophile, which is what we have in our starting material, for what will become an O-, and a C- is way less stable than an O-, and therefore Grignards will react with esters the exact same way that they would react with acid chlorides. And so I would end up with this guy if I attacked once, but then we would get another attack of the same molecule, assuming you had excess. And we would get a second attack, leaving me with two benzene rings attached here, and an O-. And if I wanted to protonate that, I could throw it in a little bit of dilute acid or water or something like that. So therefore, this kind of reaction would happen the exact same way, and the same thing would happen with excess RLI. Right, so we do these in kind of, this is step number one, and then that second step would be protonation with a little bit of dilute acid or something like that. And that would just turn that guy into the alcohol. So that's the same thing that we have seen, and that's the same thing happens with acid chlorides and esters. Likewise, if I want to add some hydrogens, oops, put an oxygen in there, I could use my lithium aluminum hydride. Lithium aluminum hydride is the strongest hydride that we have. It will react as if it is H-, and the mechanism will be the same. It will attack and kick electrons up to the O. They will slingshot back down and kick off that, basically break apart that ester, and would leave us with a new hydrogen bound, therefore making an aldehyde. And then assumedly I have extra lithium aluminum hydride, and that will react like an H- all over again, and it can react with this carbonyl, which is specifically an aldehyde, and it would add in a second hydride and give me an O-. And at that point I can protonate this guy as well if I'd like to. Usually that's your second step, is to protonate it just like we did above. Add a little bit of a dilute H+, and we will turn it into an alcohol. So there is a difference between this alcohol and this alcohol, as you can see from the structures above them. In terms of these reactions, the ones with esters and carbon nucleophiles and hydrogen nucleophiles, there is one major difference that sets them apart from the reactivity of an acid chloride, and that comes with sodium borohydride. So the other three react with an ester the same way they react with an acid chloride, but sodium borohydride reacts very slowly with an ester. And so we can be very judicious with that sodium borohydride. That is to say, we can choose and be selective of where it's going to attack, because it'll attack at that ester so slowly. So if I was to add a compound like this one, which has both an ester and a ketone, or if I was to add something that had both an ester and an acid chloride, what we would see is that adding sodium borohydride, assumedly I only add a little bit of it, so I would be very careful in adding my sodium borohydride, it would react at that ketone, or at this acid chloride, much more quickly than it would react at the ester. So there can be a reaction between sodium borohydride and an ester, but it happens so slowly that if there's any other competing location for that sodium borohydride to react, that is to say any other electrophile in the molecule, it would attack at that spot first. So my borohydride, in this case, would definitely attack that ketone first and leave me with the ester would still be there, but I would only reduce that ketone. Likewise, if I am reacting it with this compound on the bottom, it would react with that acid chloride first, which would give me a new aldehyde but leave the ester intact. So, in both of these cases, sodium borohydride will leave the esters alone unless the ester is the only functional group with which it can react. All right, so these are the addition-elimination reactions when we look at esters plus relatively strong nucleophiles and strong electrophiles. So let's move into some other conversions. We've seen previously that when we're comparing the relative stability of these molecules, that is to say these acid derivatives, that the carbonyls attached to better leaving groups are more reactive, and so kind of the king of those is the acid chloride. The acid chloride can easily be converted into an anhydride, or into an ester, or into an amide, or into a carboxylic acid. But the ones down here at the bottom are more stable, therefore less reactive. So most often what we'll do when we're trying to interconvert these molecules would be to start with the carboxylic acid, turn it into the acid chloride using thionyl chloride, SOCl2, and then we can go from the acid chloride to any of the other molecules that we'd like. But down at the bottom we have something else that we can do to interconvert these more stable acid derivatives, and that's what we're going to be looking at right now. Going back to our esters have relatively low reactivity. It's hard to kick off that OR group for a couple different reasons. One is resonance, and the other is that OR just isn't a very good leaving group. So one of the things that we can do to make this more reactive is to put it into acid. A little bit of acid will protonate the oxygen on top, and therefore we can turn it into something that looks like this. Now that oxygen has a plus charge, and it makes that carbonyl even more electrophilic. And in doing so, that guy is primed to react. And we can do this exact same thing to an amide or to a carboxylic acid, and as it turns out, we can convert that carboxylic acid into an amide, or back again. We can convert the carboxylic acid into an ester, or back into a carboxylic acid. And we can also go from an ester to an amide. We can do all of those reactions in the presence of acid relatively readily, because that acid will protonate the oxygen at the top of the carbonyl and make that carbonyl more reactive, and therefore we can kind of go back and forth on all of those. So let's look at some examples. If we start with that carboxylic acid, or excuse me, that ester the way that we've done up there, and we add in some acid in the presence of water, note that all of these steps will be reversible. water can attack that guy, kick electrons up to the O. That will give us this intermediate species that has an OH on top that's now neutral. We're going to have basically a new water attached down here that's positively charged. We're going to have an OR. So at this point, we have plenty of water sitting around in solution. Water can deprotonate the acid, or the OH down here, so it can take a hydrogen off, and because we're in acidic conditions, we can also protonate up there. So instead of drawing that as two different mechanisms, I'm going to use this shortcut. Looks like a tilde H plus, essentially meaning a hydrogen shift. And the hydrogen doesn't really move over, but we can take a hydrogen off of this spot, and we can add one on to that spot. And so we could longhand that mechanism, but I think you get the idea. And so as a result of this, if we deprotonate that OH2 at the bottom, it would just become an OH. If we protonate that OR, it would become an OR plus. And so now what happens is that oxygen's a very good leaving group. So you'll notice that in all of these intermediates, we have a species that is charged, a species that is charged positive, and another species that is charged positive, because we're essentially just shifting that hydrogen around, and that's what these guys can do, is they can shift it around however they'd like. Well, at this point, we have a very good leaving group in that O+, so for one of these OHs, the electrons can come back down again and kick that guy off, which would give us a close to a final product. It would look like this. I now have a plus charge there, an OH here, and I've kicked off an alcohol. Well, now we would use solvent to deprotonate that hydrogen up there, essentially deactivating that oxygen. So it goes from a plus charged carbonyl to a neutral carbonyl, and I've converted this guy to a carboxylic acid. So through this long mechanism, all that I've done is acid-base, nucleophile-electrophile. This is just acid-base, and acid-base again. Oh, and now I'm bringing electrons down and kicking off a leaving group, and then acid-base all over again. And what I've done is converted this OR from an ester into the OR of a carboxylic acid. And we can do the same thing with an amide, and we can do the same thing going in the reverse direction. So if I wanted to take this thing backwards, I could start with this carboxylic acid, and I could add a hydrogen up here, which would give me this species. And at that point, I've got an O+, meaning that that carbonyl is very electrophilic, and the alcohol could attack, which would give me this guy. I could shift a hydrogen around to make that OR neutral and one of those O positively charged. At that point, I could bring electrons down and kick off that water, which would give me this species, and if I just deprotonate that OH up here, I would go back to the ester. So this entire mechanism is reversible, and this is often called the Fischer esterification, going in this direction, because this is one of the first ways that we figured out how to turn a carboxylic acid plus an alcohol into an ester. But largely this mechanism is governed by Le Chatelier's principle, which is to say that if you have an ester plus water under conditions of acid, and you're turning it into a carboxylic acid plus an alcohol, that if you add a lot more alcohol, you would push the reaction back towards your starting materials. If you add a lot more water, you would push the reaction towards products. So we can kind of, even though this reaction is in equilibrium, we can choose to push it one way or the other based on how much alcohol or water or amine that we added if we wanted to push this guy towards, let's say, an amide. And so making an amide from either an ester or a carboxylic acid follows the exact same procedure, follows the exact same mechanism. So this one right down here is noticeable, as this is the way that we would turn a carboxylic acid into the amides that make the peptide backbone of proteins. So all of these are biologically relevant because having a little bit of acid and converting esters and carboxylic acids and amides is something that we do in our bodies all the time. We will never have acid chlorides in there, and we don't have any thionyl chloride in our bodies, so turning these guys back and forth using an acid catalyst is oftentimes what enzymes will regulate. So in all of these mechanisms, essentially the energy looks like this. You're starting with something relatively stable, whether that is an ester or an acid or an amide, and you're basically just going back and forth between two relatively stable things. That was not the case when we started with an acid chloride, which starts off at a very high energy place. So at this point, we've seen that we can convert an acid chloride down into any of these things. We can basically go sideways to turn an ester into a carboxylic acid or an amide, but let's move on to look at transesterification, which is where we can turn an ester into a different ester. Transesterification looks just like that conversion that we had on the previous slide, but let's give you a specific example. So let's say I have an ester with essentially this 3-carbon oxygen chunk right here. Maybe I want to convert that into a methyl ester instead. I could just add CH3OH. Under conditions with a little bit of acid, again usually using something like H2SO4, I could basically swap those two things out. So I can put the OCH3 onto my ester, and I would remove that propyl oxygen group as my alcohol. So you can see that all I've really done here is taken that yellow 3-carbon fragment off and replaced it with that 1-carbon blue fragment there. So this is called transesterification. And because one of the major classes of biomolecules is a tri- or diester, we will see that this has a lot of uses both biologically and in terms of molecules or reactions that we can do outside of the body using biological starting materials. So we will talk about that in class, but please practice this. If you have any questions on any of these reactions, please bring them with you to class, and I will be happy to answer them. Go Bears!